Discretization can also be a name which is used for the process of meshing a structure for finite element analysis. Now, what does meshing actually stand for? Meshing stands for distributing or actually dividing a structure into a number of smaller parts. And depending on the kind of structure it is, the parts are can be of a certain dimension, and those are actually elements. So the entire process of, first of all, dividing a structure into smaller parts and then deciding where exactly these smaller parts are, where do they join each other, where do you want the nodes to exist, comes under meshing or discretization. So under the topic of meshing, we have to know certain things. First of all, we should already have decided the type of element. So that means we already know the type of element that is going to be used to mesh a certain structure. How do we decide what kind of element that we have to use? That would completely depend on the structural application and what kind of results we want to see from the structure. Now, if I want to just see a certain truss element or truss assembly, so let's take example. So I'm going to take examples now of the kind of structure and how do we decide element type. Element type decision. So if we have a truss kind of a structure, yeah, we have something like this, and we have a load acting here, and we have a certain boundary condition here, and we want to find out all the unknowns in this problem. Yeah, so we know that this is a truss structure that is given to us. Yeah, we know some conditions. This is a truss, and all the motion or the deformation that's going to happen in the structure is always going to be in the direction of the trusses. So everything basically can be idealized as 1D elements. So if they're all 1D idealization, that means the element type we can already choose to be truss one-dimensional elements. That's quite easy. In the same way, if I have a cantilever beam, yeah, I have a cantilever beam which is fixed on the left edge, and I have a load on this side, it's a point load, then I know from my experience that it's going to bend like this. Yeah, there'll be a vertical displacement, and we know that if we want to check what kind of stresses are arising everywhere, those axial stresses, and what kind of bending happens, then we will be able to idealize it also as a beam. So we can say, okay, it's a beam, and it's enough to know because the cross-sectional area is much smaller than the length. It can be idealized again as a beam 1D element. So that was quite easy because this is what exactly we are looking for. Now, for example, if I change, as a third example, I want to change this cantilever beam problem, and I want to say that it's a short beam, it's that short. Yeah, now I have force acting here, there's a certain area of cross section over here, and it's not very much smaller than the length, the dimensions. So in this case, I would want to consider it as a beam, but I may not be able to idealize it that easily as a beam element because it doesn't check out with the Euler-Bernoulli principle. So what do I do then? Then I can't simply say this is a beam one-dimensional element. This becomes complicated. So if I now make an enlarged view of this structure, then it's going to end up being a three-dimensional beam like this, which we know is fixed at this end. And this sort of looks accurate. So I have a certain load acting over here, and it quite much looks like a cube to me. So that means if the dimension of the cross-sectional area here is not very much different than the cross-sectional area at the bottom, that means the length is quite short, and the cross-sectional area is, again, it's not making it reduced to a 1D element, which is already clear, but it also can't be made into a 2D element because the 2D element has to be planar. That means we are not going to consider the thickness at all. So it cannot be 1D, it cannot be 2D. So the only option we have left is to choose 3-dimensional elements. And we can quite easily make this with 3-dimensional elements. It will be very accurate. We'll get all the results that we need. So we've made a choice of what kind of element we can use. So that completely now depends on the kind of structure that we have at hand. Yeah, let's also look at one extra complicated structure. Because so far we only thought, okay, 1-dimensional elements, we have 2-dimensional, we have 3-dimensional, but you can also have complicated structures such as the aircraft wing, let's take the aircraft wing. Somehow it doesn't want me to. That's very slender wing. Now inside the wing, I will have a wing box. Then I have the leading edge, the trailing edge, and then I have flaps, and then I have slats and whatever I need. If I look through the cross section and I pick out a certain section of this wing, so we are looking at a wing. This is the cross section. Now if I look at one of the panels between rib to rib, so if I have rib to rib here, so I have rib 1, and I have rib 2, and I take out this section here, and I draw it out, then I have a skin. So this happens to be a skin. On the skin, there are certain longerons. So we have some stiffening elements. Let me draw it with a different color. So these are stiffening elements. Let's call them stiffeners. These stiffeners can be of a Z cross section, they can be T cross section, they can be I cross section, they can be C channels. Yeah, but in general they are beams. So what you see here, if you want to idealize this particular structure and want to put it in finite elements, then we have a skin which has certain characteristics. That means it is thin, it is plane, so it can be idealized as a 2-dimension. And on the other side you have stiffeners which have a beam cross section, and they have a length which is much greater than that of the cross-sectional area dimensions. So we can idealize them as 1-dimensional beams. Right? So we also have structures which will have more than one kind of elements in the same structure itself, in the same part. And that's the nice thing about finite elements. We can very easily combine different kinds of elements. Of course, there is a question of mismatching the number of degrees of freedom among different elements. But this problem can be solved by using some smart choices. And we will go through this in the last week of the course. We will try to model a skin with the stiffeners on it, and we will see exactly how we have to make some design choices in finite element design, so we know that we are constraining the right kind of degrees of freedom, so we don't cause a mismatch in the number of degrees of freedom where two different kinds of elements are overlapping or meet each other. So this was something about how do we decide on the kind of element depending on the structure that needs to be modeled and analyzed using finite element analysis. One small remark at the end: always remember that your element choice also dictates what kind of results you can get. If you want to look at results that are in the 3 dimensions in out of plane direction, then a plane element like a 2D element won't be able to help you much. So you will have to go into the 3-dimensional. But there are ways of simplifying your model in such a way that you don't need to go into the 3-dimension and you can make do with 2-dimension. So there are interchangeable choices, and that is something that you will have as a toolkit at the end of the course. So always make sure that the type of element is decided based upon the structure and what exactly you want to see as a result after the analysis of that structure.